Hello, and welcome to Math 433. Today we're going to talk about page 92 in our textbook and following, which is section 3.5, multivariate distributions. And the idea is that we've got two random variables, x and y, and we're looking at the distribution for the two random variables. Nothing very unusual about having two random variables. If our experiment is to pick a human being out of the population, we may have a random variable x that would measure that person's height and a random variable y that would measure that person's weight. Those would be continuous random variables, and before we do the continuous, we want to take the somewhat simpler case of discrete random variables. So as the example, let's not use weight and height here. Let's use the outcome from rolling a die. Roll a four-sided die, though. That way I don't have to write so much. Now, there are four-sided die. They're tetrahedrons, like that, and there's a hidden face over here. All faces are equilateral triangles. And when you cast this die, now all of these faces are exactly the same. The face that's down is the one that, quote, shows. And the faces are usually labeled 1, 2, 3, 4. And then I want to also toss a coin. And that coin will come up heads or tails. We know that. Now, just to make it interesting, I want to think about the die and the coin neither being fair. So they're loaded. So here's the loading. Let's let x be what happens on the die, and y can be what happens on the coin. So x could be 1, 2, 3, 4. And p of x, now we're assuming that someone has altered this, this coin, and so these are not going to be in lowest terms, but let's suppose that the probability that it comes up 1 is 2/16 and 3/16 for 2 and 4/16 and 7/16, and you know that has to add to 1 if we've done it correctly. So we've got 5 and 4 is 9 and 7 is 16, adds to 1. That's good. And then the y would be heads or tails, and it's not a balanced coin either. So p of y, just suppose, is 3/4, 1/4, and we want to consider the joint distribution. Well, we could put the joint distribution into a table, and if we did, it would look like heads, tails, 1, 2, 3, 4, and just to make it easier visually, well, these are not very straight lines today. Let's make it look like that. So what I would fill in here would be the probability of the coin coming up heads and the die coming up 1. So right here we would have the probability that, let's do the row first, that the coin, no, that's not right, coin. We made coin the the y variable. So this would be y equal 1 and x equal heads. So these would be independent events. The die doesn't know what happened to the coin, or the coin what happened to the die. So this would be equal to the probability that y is equal to 1 times the probability that x is equal to heads, would be equal to 2/16 times 3, 4 equals 6/64. 6/64. Now, I want to fill out the rest of the table the same way and calculate these probabilities, and they're going to be 9/64 and 12/64 and 21/64. A good exercise would be for you to check me on this. 2/64, 3/64, 4/64, and 7/64. And you see that I didn't reduce those fractions, and it was a good thing because it makes it easier now to do some computation with them. Get a color that I like here. Well, a couple things that we would notice. For the joint probability distribution, these probabilities have to add up to 1. And I can symbolize that if you add over all the x's and y's, p x equal x, y equal y. If we've got a proper probability distribution, a joint distribution, that has to add to 1. So let's see real quick if it does. Now, probably the quickest way is to add this column and then add this column. So we've got 6 and 9 is 15, 25, 27, 28, 38. I think I did that wrong. Let's try it again. 15, 27, 47, and 1 is 48. 48/64. And this side would be 2 and 3 would be 5, 9, 16/64. And if I add these two up, then I'm going to get 48 and 16 is 64/64. So they add to 1, and that's the sum of everything in the table. So it satisfies this condition. Now let's add a cross also. And if we add a cross, we get 8/64. 12/64 is what this would be. 12/64. 16/64. And 28/64. I'm going to change color again. And now I want to reduce these to lowest terms just for illustration. So 8/64 would be 1/8. And 12/64 would be 3/16. And 16/64 would be 1/4. And 7/16. And 3/4. And 1/4. So a reason for doing this is I want you to pay attention to this, because this is called the marginal distribution. And what did we call the coin? This is the marginal distribution for y. And this piece is the marginal distribution for x. Now compare these two marginal distributions to the original distributions for x and y. And I don't know if that surprises you or not, but they are, in fact, they're the same. So the marginal distributions would be the distributions for the random variables alone, and the body of the table would be their joint probability distribution. So there may be something sacred about short videos. This thing has gone 11 minutes. I guess I'm going to try to end it here and see if that's considered better practice. And so we'll pick this up in the next video. Thank you.